Hello, and welcome to our Notes 2.2, where we're going to continue talking about random variables, but this time we're talking about continuous random variables. So unlike discrete random variables that can only take on specific, certain, distinct values within a range, a random variable that is continuous can take on any numerical value in a range. So examples like this would be height. We might boil down someone's height to 5'4", but the reality is that we're just sort of rounding that because they're probably 5 feet 4 and 3/8 inches or something like that. So there's a lot of different values that can happen. Weight is similar. Again, we might boil it down. You're 180 pounds, but you're really like 180.3724 pounds. Grade percentages, those are another thing. Again, you might see in Schoology it says I have an 87%, but the reality is that if you calculate it out, it might be 87.284. Like there's really an infinite number of heights, weights, grades that things can be because of how they work. They're continuous. When you're also thinking about like at some point when you were a baby, you were like 3 feet tall. Not a baby, but like as a child, you were 3 feet tall. Now you're the height you are. You hit every single height in between that. And there's an infinite number of heights. You've been an infinite number of heights in your life. Think about that. So that's what continuous means, is that it's not just these specific values, it's a continuum. So one of the things that's going to help us here with finding the same sort of things we wanted to talk about with our discrete random variables, which is like, where is it centered and how is it spread out? Well, one of the things we're going to utilize a lot are z-scores, standardized scores. So we're going to do a quick example of this. If you've ever forgotten what a z-score is, it is on your formula sheet. So if you go all the way down to the bottom of the first page here, it says right here, standardized test statistic. So an example of a standardized test statistic, that's a tongue twister, standardized test statistic is a z-score. There are other things we'll learn about in the future that are also denoted with a lot of letters. But that's the idea, is that you take sort of your statistic or observation. You're going to subtract it by sort of the parameter, what you believe about the population is to be the center, and divide it by the standard error, standard deviation, in our case, of that particular statistic. So the language is a little bit different here, but that's the idea. Observation minus mean all over standard deviation. So let's do an example of that. So here we have the heights of men worldwide has a mean of 69 inches with standard deviation of 4 inches. The tallest recorded man in history was a man named Robert Wadlow from Illinois. He was 8 feet and 11 inches tall. We want to find the z-score for Robert and then interpret the meaning of the z-score. So first, what I want to do with this is I'm going to take this height of Robert and I'm going to convert it into the units that I have sort of my population parameter info all about in, which is just in inches. So it turns out 8 feet 11 inches is 107 inches. And then I'm going to go ahead and use sort of that formula for z. So z, that is going to be our observation of 107 subtracted by the mean of 69 all over our standard deviation of 4, which gets us 9.5. Remember, there's no units on a z-score because the units in the numerator is inches, and the units in the denominator is inches. Inches divided by inches is unitless. So how do we interpret that? Well, z sort of tells us how many standard deviations we are above or below from the mean. So in this case, 9.5 being a positive value means we're above. So we would write that Robert is 9.5, 9.5 standard deviations taller or above than the average man. There are a lot of ways to write that, but that's the idea of how I'm going to write it there. So cool. so that is z-scores as a review there, so that way you're ready to rock into what we're about to do, because we're going to take z-scores and we're going to go one step further with it and talk about probabilities with it. Because everything dealing with the z-score that we usually deal with is centered around this idea of something called a normal model. So what is a normal model? A normal model is a distribution that's roughly bell-shaped and unimodal symmetric. Bell-shaped, unimodal symmetric. What does that mean? Bell-shaped, you might have already heard, but we know what unimodal symmetric is all about. It has one peak, and it's roughly symmetric. There's no heavy skewness going on with it at all. It's not bimodal, several humps in the data. So it is, this sort of just kind of like single mountain. You'd sort of imagine it just sort of looks something like that. And so that's what we would expect it to see in these particular cases. And a lot of things in the world are normal. There's also a lot of things that are not, which we'll have to get into later on in our sort of unit here. But for now, we're going to be dealing with things that are roughly symmetric and unimodal and thus roughly normal. So how do you check if something's normal? Because what we're about to do here is all about, you got to know that it's normal in order to be able to use the tools that are coming forward in these notes. Well, you can check the nearly normal condition. It's not a very clever name, but that's what they've decided. In other words, what you're checking is that the shape of whatever distribution you're dealing with is roughly symmetric, roughly bell-shaped, unimodal, so that way you know it's okay to use a normal model moving forward. And the importance of the normal model comes up on the backside of this page. But for now, we're going to figure out, well, how do you check if something's normal? There's 3 ways to do that. The first one is the easiest and pretty common, which is they'll just tell you flat out in the problem that it is normal or approximately normal, or that you can use the normal model. And so as soon as they say that, check, move on. All right? But there are other ways. If they just give you some data and you're like, I think I want to use the normal model, don't just jump in and just assume you can. There are 2 ways to check. The first one is you can make a display of the data. So a histogram or a stem and leaf plot. Histogram, obviously, you can do with your calculator. Stem and leaf plot, you'd have to do by hand. And you're looking to make sure that it is roughly bell-shaped and unimodal. So that's my preferred way, but there is another way that your calculator can do for you, and maybe you prefer this, is you can make a normal probability plot, okay? So a normal probability plot tries to sort of plot the values up against sort of z-scores and see how does it work out. If it is in fact normal, then it should be relatively linear, relatively straight. We're not going to go too much into what a normal probability plot is and how it's graphed. If you're interested in it, go ahead and seek out some extra info, or maybe we'll put some stuff in our resources. But for the most part, you just need to know how to use that tool, which is when you plot the data, you should be looking at something that's relatively straight. So let's do a couple of examples here where we're going to look at these things. So I have here 15 data points in this first box here, and I'm looking to see, is this data nearly normal? Well, since it's just data, they didn't mention that it is, I have to go and check. The first thing I can do is make a histogram. So let's make a histogram of this stuff. So just a quick refresher on making a histogram. So I put all the data here into list 1, and then I'm going to hit second stat plot and go to that first plot there. It's on already. If it's not on, turn it on. I'm going to go over here and type and go to the histogram and hit enter. All my data is in list 1. The rest of that looks fine, so I'll hit zoom 9. And there's the histogram of the data, which when I'm looking at it, I can see has a single peak, so unimodal, and roughly symmetric, roughly bell-shaped. So right now, I am not thinking this is crazy skewed, so I'm sort of in the boat of nearly normal. So the histogram looks something like this. And so I just jot it down here in our notes. You should copy it down too, but we decided, yeah, that looks unimodal, roughly symmetric. It doesn't have to be perfectly symmetric. All right, how about this normal probability plot? How do we do that? Well, let's take a look at how that works. So let's see how we make a normal probability plot now. So again, make sure all your data is here in a list. I have it all in list 1. And just like we were doing the histogram, we're going to go back to stat plot, press enter. And this time around, when we go down to type, we're going to go to the very, very last one. This weird like little step thingy. Kind of seems like it's like, is that like a histogram? A scatter plot? No, the first one's a scatter plot here. That one is our normal probability plot. So we're going to hit enter and it pops up with some extra stuff here. Data list, we're going to keep all my datas in L1. Data access, I like to keep it as X. It really shouldn't matter. We should see a straight line if it is actually normal-ish. No matter what, I would just keep it at X. And then just as we usually do, I'm going to hit zoom, 9, and there you have it. So that is our normal probability plot. And it looks fairly straight, fairly linear. It's got a little wiggle in some places, but not enough to me to be scared. So again, I'm getting some evidence pointing to that I believe our data is nearly normal. So take a moment to go ahead and just sketch out the normal probability plot. It doesn't have to be perfect here. I'm not even bothering with scales here, but we can see that this is following a pretty straight line here. So in conclusion, I would say that both show that this data has a nearly normal distribution. So all the tools we're about to learn on this backside could totally apply to this set of data. So why don't you go ahead now and test it out on the other set of data. So I want you to create a histogram on your calculator and a normal probability plot, sketch them in there, and come to your own conclusion. All right, so we're going to go ahead and move on to some notation here. So normal models, we can write normal model with mean this and standard deviation that, but there is some shorthand that we can use as well that we might see as we kind of go along here. And it really emphasizes, I think, the fact that normal curves are like a family of functions. In fact, there are ways to create equations of normal functions. And you could look it up later if you wanted to. Not important for this. Important if you're going to do the calculus behind all of this. But these are just a family of functions that get centered at different places and spread out in different ways. And so because of that, we can sort of, like we would, with the quadratic functions, just sort of like, oh, I can move it left, right, up, down. I can dilate it this way. You just throw in some new numbers. This one only has 2 parameters. So it's actually closer to like a linear function. All lines are the same except some of them have different slopes and y-intercepts. Here, we're going to have different centers and spreads. So we can note it with this, capital N, and then parentheses, mu, comma, sigma, where mu is the mean, and sigma is the standard deviation. And so that means that anytime something says it's normal with these mean or standard deviation, a shorter way that you could write it would just be here. So we have here that's a in parentheses 210 means it has a mean of 200 with a standard deviation of 10. Over here we got a normal model that has a center at 3 with its standard deviation at 0.5. So we could use that notation as well. That's just a little bit shorter. So if you ever see that, it means it's telling you the mean and the standard deviation. So let's move on to some tools. If we know things are normal, what does this mean? How come that's important to us? Well, there's 2 really important things. One of them might have been something you had previously learned in another class, called the empirical rule, sometimes called the 68, 95, 99.7 rule. It's called that longer number version because the number of standard deviations away you are from the center of a normal distribution tells you what percentage of all the values you can find within that. So here, in a normal model, if we are 1 standard deviation from the mean, then that means that 68% of our observations fall within that. So in here, that is 68% of the data there. And you can see that it is split evenly, because if a normal model is perfectly symmetric, theoretically, then that means to the left of that mean, we have 34%, and on the right side, we have another 34%. It won't work out perfectly with real data, but theoretically it should. Continuing along, if we are 2 standard deviations from the mean in both directions, then that's going to be a grand total of 95% of our data. And you can see again the symmetry going on, 13.5, 13.5. So that's almost all of our data. In a normal distribution, almost all of our data is 2 standard deviations from the mean. Having a standard deviation outside of 2 kind of puts you into a special, unique category almost. But even more so, if you are 3 standard deviations away, then that is 99.7% of all observations. All of your data lies within 3 standard deviations. Not quite all of it, but just about. In a small enough data set, it could be that it is all of it, actually. And then we don't really care too much about going beyond that. So beyond 3 standard deviations is very rare in a normal model. And it does happen, but it's not something we attach to specific rules. Theoretically, the normal model extends to infinity. Theoretically, you could think about, a standard deviation 9.5 above the mean and be able to sort of think about, well, what percentile does that put me in? But the rounding becomes so close to like 100% that we don't go past that. So let's do a couple of examples here. So what percent of the world's men are between 5'1" and 6'5" is our question. Well, before I even get into that, what I like to do is sort of draw myself a little miniature model here. So I'm going to go ahead and draw a little normal curve as best I can. I'm not very good at it, but I try my best. And I'm going to label it according to the information we had on the previous page. On the previous page, it said that my mean for men height was 69 inches with a standard deviation of 4. So I'm going to come along here and I'm going to mark out 3 standard deviations this way, 3 standard deviations that way, and label them. It's going to get really obnoxiously tight here. Should have drawn it a little bit wider, but it's fine. You get the idea. So I'm labeling by 4s because that is what the previous information had given me. And so this is heights of men in inches. All right. So let's think about this again. What are they asking? Percent of men who are between 5'1" and 6'5". I'm going to convert to inches. So this we know is 61 inches. 6'5", that's going to be 77 inches there. So then I'm going to come over here and take a look-see and go, okay, 61 right there. 77 right there. Cool. I'm going to actually draw that sort of a little bit higher. So that right there, how many standard deviations away is that? Well, that's 2 to the left and 2 to the right. And according to my empirical rule up there, that means it's going to be 95% of my data lies within 2 standard deviations to the left and right. All right, that was a simple one. How about this next one? Cristiano Ronaldo is 6'1". What percent of the world's population of men is shorter than he is? That's a different question there. All right, well, let's go ahead and figure this out. 6'1", okay, that's going to be 73 inches. And that's right here. But this time I'm not interested in between here. I'm actually interested in all of this. I want to know, what is all that shading, all that percentage there to the left of that? Why don't you take a moment and see, can you figure out what percentage that's going to be, and how does that make sense? So the way I'm going to figure this out is actually utilizing the fact that this is theoretically perfectly symmetric, which means that from 69 inches and below, that should be 50% of my data. That's the mean, and since it's perfectly symmetric, that lines up with the median as well, which means it is perfectly 50 percentile or 50% of our data. So all I really need to think about is like, well, what is all of this over here? And I can look up at the diagram up above to help me out with that, but I also know that one standard deviation gives us 68%, but I'm only looking at half of that, so that would be 34%. So in the end here, I'm going to end up with a total of 84% of all men are shorter than Cristiano Ronaldo. So that's how you can sort of play with these percentages. Sometimes you got to chunk them up to try to figure it out. Sometimes it's thinking about, oh, there's 100% under it all, but I'm just subtracting off this amount. So you got to sort of play around with those things sometimes. All right, so a good question you might have here is like, well, what if some of my observations I'm looking at don't land perfectly and beautifully on a standard deviation like yours did, Mr. Schulten? These two questions were nice and all, but like, what if I wanted to know what percentage of men are shorter than 66 inches tall? Like, I could guess at it? No, we're not going to guess at it. We're going to utilize something called a z-table to help us out with this, and our calculator, actually. Because what we can do with all of our normal stuff is we can actually transform this to create something known as the standard normal model. A standard normal model has been transformed by the mean over, so that way it is at 0 centered, and then been divided by the standard deviation of the whole population, so that way we have a standard deviation of 1. So we're a mean of 0 and a standard deviation of 1. So let's sort of jump into another example and see where the empirical rule sort of fails us and what our new tool is. So Lionel Messi, that's another soccer player. He is 5'7". So what proportion of men are shorter than Lionel Messi? Well, let's do what we did before. Let's first find our z-score here, like we did with Robert Ladlow. So Messier, 5'7", that's going to be 67 inches. So we got 67 minus the average is 69, all over a standard deviation of 4, which gets us negative 0.5. And so again, if you were like trying to go for like the idea of using the empirical rule, you'd look over here and go, well, 67 inches falls halfway between 65 and 69. So do I just like take the average? No, it's not a linear function. You can't just take an average of percentages and have it work. We have to have something else. So what is our something else? Here's what our something else is. It's something known as the z-table. I'm going to show it to you really quickly, but we're going to do something slightly different in a moment. Here's your z-table or z-score table. So here, this maps up different z-scores with different proportions. Instead of needing to rely on landing perfectly 1 standard deviation or 2 standard deviations, this one gives us sort of in-betweens. What if I'm 1.29 standard deviations? Well, 1.2 is right here, and if I follow it along, this column is the 0.9, so where they intersect, that would be sort of the proportion, the percentage I'd be looking for. Oh, that's awesome. I agree with you, student that is not currently here. So let me show you how we would use this. What I still like to do is I like to draw the normal curve, the standard normal curve. So I'm going to do that right below here. Again, kind of squishing it in there, but it's standard, so I don't have to worry about like adding up and subtracting by 4s to try to come up with the values here. I'm just going to go with centered at 0, standard deviations of 1. And the reason I can do that is because I've already calculated that Lionel Messi is at 0.5, negative 0.5. So that means Lionel Messi is like right here. And I want to know what proportion of men are shorter. Oh, that's all over here. So how do I use that table you just showed, Mr. Schulten, to calculate that percentage, that area that you just shaded in there? Well, we're going to look for a z-score of negative 0.50. This always rounds to 2 decimal places on this table, and that's why we like to round to 2 decimal places when we're finding z-scores. In this case, the second decimal place is a 0, but that's actually helpful here. So let's take a look through. I'm going to start finding negative 0.5. So I'm in the negative 3s, the negative 2s. You can see they don't go far past those. Remember, these are very uncommon occurrences, being more than 3 standard deviations away. Keep scrolling, and then bam, here it is, negative 0.5. And what's the second decimal place? It's 0, so I'm looking in this column here, scrolling down, and right there. That is our percentage, our proportion of men that fall below Lionel Messier's height. Or more generally, that is the proportion of area under the normal curve that is under half a standard deviation to the left. It's the same for all normal curves. A half standard deviation to the left has this particular percentage associated with it. So let's write that down here. The way we would write that down, being all fancy, now that we know our probability notation, is we would write the probability that z is less than negative 0.50 is equal to, it said on the z table, 3085, or about 30.85%. So there you have it. That's how we use that z-score table to help us out with things that don't fall nicely 1, 2, 3 standard deviations away. I really like using the z-table. It's something I'm really comfortable with. But you might be wondering, well, does my calculator find this for me as well? And it does. Let me show you how to do that. And so now let's take a look at how we can find our percentage proportion for under a normal curve using our calculator. So like I said, I like to use the z-score table pretty frequently. It's a comfortable sort of use for me. But if you're someone that's is a little confused by it, I hope you gain confidence in it, but your calculator can check your answers for you as well. So to do that, we need to go to a brand new area in our calculator that we haven't been to before, called the distribution menu there. So it's here. The vars number in blue, you can see it says distr, which stands for distribution. So to get there, we're going to go ahead and press second, and then that vars button. And then it has a huge list of distributions, most of which we will end up using at some points during this year. And the one we want is the second one here, normal CDF. Normal PDF is pretty useless to us in this class. What it kind of does is sort of tell you like where you can plot points, like in terms of like if you were trying to create the normal distribution by hand. It's actually pretty helpful if you were trying to actually make a normal distribution on your calculator. If you're into programming and you're like, ooh, I want to put up like a display up here that shows the normal distribution and shades in for me, you could program that and this normal PDF would be helpful for that. But we're going to always use normal CDF. You might be wondering what's the difference there. PDF is sort of a point distribution function, I want to say. Well, we want a cumulative distribution function. We want to sort of add up all the area underneath. So when you hit enter, if you have a new calculator like mine, this menu pops up. If not, it might just say normal CDF, open parentheses, and it's blinking at you to enter some stuff. You're going to enter the same things I'm going to enter, except for you're going to separate each thing with a comma. And if you're wondering, where's the comma? It's right above the 7 right here. So the first thing we're going to enter is the lower bound. We know that the normal curve extends to infinity in both directions. So how do you write infinity? Well, one way you can sort of do it is like what they've already given you here, -1, and that's scientific notation, times 10 to the 99th power. So that's a -1 followed by 99 zeros. That's pretty far out there. Another way, if you're ever sort of doing it, because sometimes going to find this scientific notation button is a little annoying. What I'll do is I'll just hit -9999999, and then I'll just keep pressing 9 until I'm bored. And then I'm like, great, there we go. That's not as big of a number as the one that was in there before, but it really will not change things. All right, so if you have an older calculator, here's where you'd hit comma, and then upper bounds. Well, we do have an upper bound for Lionel Messi. It is going to be 67 inches. So we'll type that in. You could have also typed in the value of the z-score here. So if you wanted to actually keep everything, you'll notice that right now it has a mu of 0 and a sigma of 1. So if I just type in -0.5 right here, I'm done and I can go to paste. But I'm going to actually type in the original info just in case I messed up my z-score, just in case. So enter. Mean is 69 inches is what they told us. Enter. Again, every time I'm pressing enter, other people, you're doing a comma. And then it's a 4-inch standard deviation. And I hit enter again, and I'll paste it. And so people that were not seeing that menu, you should be seeing what I'm seeing right now, a bunch of 9s, comma, 67, comma, 69, comma, 4. And then I hit enter. And there you have it. I've got 0.3085375. It gives us more decimals because it can be a little more accurate since it's a calculator and not just a table of values, but we can see that it does in fact match our first 4 digits. Sometimes you might be off a little bit, Z table compared to your calculator, but it shouldn't be vastly different. If I got 0.3084, I wouldn't be too upset, but if I got 0.3182, then I'd be like, I think I messed up something. So that's how you use your calculator to find area under a normal curve. So to just sort of debrief, sort of the notation behind that is you want to go into your distributions, you're going to find normal CDF, and then the things you're plugging in is you're going to plug in lower bound. If it's something that is supposed to go to like infinity, just hit -9, or if it's positive infinity, positive 9. Just press 9 until you're kind of tired. Followed by the upper bound, followed by the mean, followed by the standard deviation. This is really helpful, especially if you have an older calculator, because it'll just pop up with normal CDF and then just blink at you to type in these things. So you just need to type in these parameters, separate them with commas, and then you're good to go. So this value that we found, 0.3185, that has a special name. It's called a p-value. That's the proportion or percentage of observations that are found below or under a given z-score. And that will become pretty important to us as we move into thinking about testing hypotheses. I know that you're like, that's science. What are you talking about? But a p-value is going to be really important to us when we get to sort of thinking about when do we know something happens relatively frequently or is too uncommon to just be by chance alone. So I just wanted to point out what it is now so that way we could talk about it. And it makes sense, it's called p-value because it is mapping to a probability. So there's a ton of ways that we can use this standard normal model. We're going to try them out. Well, you're going to try them out. I'll set you sort of up with some thinking here, but then I want you to try to go into your table or your calculator, preferably both, and try to figure these out here. So we have here this setup. There's a tire manufacturer that believes the tread life of its tires can be approximated using a normal model with a mean of 32,000 miles and a standard deviation of 2,200 miles. So the first question, what proportion of these tires can be expected to last more than 36,000 miles? Okay, so the first thing you would want to do here is you'd like to find a z-score associated with this, like we did with Lionel Messi. The key difference here, though, is with Lionel, we were wondering who is under him in terms of height. Notice that the wording here says more than. So the z-score table shows you less than. How do you think you're going to find more than? At the very least, finish this out and do the less than component. See if you can figure out how to answer this specific question. If not, we'll talk about it in class. Moving on to part B. Here, we got two different values. We want to know what is it in between these two. What's the probability it lasts between these two? Well, in this case, since we have two values, we probably want to calculate two different z-scores. We'll call them z1 and z2. You can call them really whatever subscripts you want. And then you're going to sort of go into the normal table and try to figure out how to use those values. You're going to do two searches in your z-score table, and then think about how are you going to use these values to figure out sort of this in-betweenness. We want to know what's the probability of falling between these two. And then the last one we'll talk about what's the IQR for the tread life of these tires. So this is using z-scores in reverse. So instead of this one being here's an observation, find a z-score, move to your z-score table, you're actually going to start on the table because they tell you IQR, which that's the middle 50%. They've given you the percentile or the proportion or the area here, and you need to use that and move back to what are some mileages we can put on for these. So this is the middle 50%. So be careful and don't just go to the 50th percentile. You want to find the middle 50%. Remember, that's 25% to 75%, quartile 1 to quartile 3. So how do you use that table starting with these percentages? Try it out, do your best, and then we'll come in and talk about this problem as well. So that's going to do it for us here. So you have these three problems to try out and work through and see how you might do on them. And you have this one here, the normal probability plot and histogram with this data and coming to a conclusion of whether you believe you are dealing with something nearly normal or not. So with those completed, you're done, and we'll see you in class.